All right, class. So in this video, I'm just going to work through a few examples of probability that you're probably seeing in the different things that you're working on this week. So just a quick overview. We're looking at rolling two dice together, sampling both with and without replacement, and then mutually exclusive and independent events. So just kind of taking a look at some of the problems that deal with those things. So with the first one, rolling two dice. Okay, so I have a question here. When you roll two dice, what is the probability that the sum of the two dice is 4 or less? And then a second question, what is the probability that that sum is odd? So a couple of ways to look at this. And honestly, now we really probably couldn't do this with something more complicated than just two dice or a coin, because then our number of possible combinations gets out of control, and we have to do some crazy math to deal with all of the combinations. But with it just being two dice, what you're going to want to do is you want to make a list of all of the different possible possibilities and combinations. So for us, right? So as an example, right, the first dice could be 1, and then the second dice could be 1. Well, then another option is you could have 1 and 2, and 1 and 3. And 1 and 4, and then, and then 1 and 5, and then 1 and 6, as our different options. And that's just looking at one. This is just one row, because the other way we could look at this is, well, we could say, well, what if what if the first dice was 2? So it could be 2 and 1, and then 2 and 2, and then 2 and 3, and 2 and 4, and 2 and 5, and 2 and 6, right? And then you have 3 and 1, and 3 and 2, and 3 and 3, and 3 and 4, and 3 and 5, and 3 and 6, and this just keeps going, right? We could finish making this list where we would have our 4 and 1, our 5 and 1, our 6 and 1, and we'd make this big table, okay? So then the next thing that we want to look at is, all right, so these are all of the total possibilities, everything that can be when we're dealing with and rolling just two dice, right? I have all of these. So how many possibilities is that, right? What is the total number of outcomes? Well, I've made a little grid here that's 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4, 5, 6, right? So 6 times 6, there are 36 total possible outcomes here when you're rolling two dice. And these are, and what I have listed here is these are all of the combinations of all of those possible outcomes. So 36 possibilities, right? And that's important when you're dealing with statistics. We have to know our number of possibilities. Okay, so that's the first thing we need. Then the second thing we want to look at is we want to find, okay, well, which are all of the possibilities that even meet the criteria we're looking at, right? So the first one is, I want a dice roll that sum is 4 or less. If you're like a Settlers of Catan player, right? That might be important to you, right? If you're deciding where to place your little settlements or whatever on the board, right? You want to know what's the chance of you actually rolling a certain amount. So we can look at this. So what's the chance of rolling something that is 4 or less? Well, so we go through and we look. So, well, the sum of this is 2, and that's 3, and that's 4, and this is 5. Well, that one doesn't work. And the other ones are going to be bigger than that, and this is going to be 3 and 4, and then everything else we know is going to be bigger, right? It's going to be 5 and 6 and 7 and 8, right? That's too big. And this one's going to be 4, and then everything else is going to be bigger, right? This is going to be 5 and 6 and 7 and 8, right? And then this one is already 5, right? So that's too big, and so at this point, right, I really don't need to look at anything else. So with the sum being 4 or less, there are 1, 2, 3, 4, 5, 6 possibilities of dice rolls or combinations that are 4 or less. So to get the answer to the first one, I'm going to take, well, here's our 6 possible options divided by the 36 total options to get our probability. Okay. And so what? This boils down to be 1/6. And then we could stick that into a calculator and get a decimal if we wanted to. Which most probabilities are written in decimals, but you can also leave it in fraction form. So that's that one. So then looking at the second one, okay. So now I want to look at what is the probability that the sum is odd? Okay, well, if I add these, well, that's 2, that's even. This one's even. This is going to be even. So I have 1, 2, 3 that end up being odd, right? Because this is 3, 5, and this is 7. And then down here, well, this is odd. 1, this is 5, this is 7. That'll be odd. The other ones are even. And if you look at this one, this is going to give me 5. That'll give me 7. This will give me 9. So if you notice, each row I have 3 of these chances that give me an odd sum as you go through and like look at all the different possibilities. Right, this one's going to be 5. The other one would be here and here. Right, and so you can see that right. I'm establishing a pattern. So what? There's 3 times 6, so you're going to have 18 chances of getting an odd out of 36 total possible rolls. So when you divide this out, this ends up being 1/2 or 0.5, right? So that's the probability of 0.5, or right, you have a 50% chance of rolling a sum that is odd. But that's something that I think we could have intuitively thought our way through. But like looking at the entire problem, you can see how it works out in this space. So whenever you're dealing with the sum of 2 dice, really the best way of looking at a problem like this is go back, list out all the possibilities, and then go through and then count the ones that meet the criteria that you're looking for. And a problem like this, because we're not using the crazy mathematics, it's going to be something simple like 2 dice or flipping a coin, okay? Okay, so the next scenario we want to look at is sampling with or without replacement. So we'll start with sampling with replacement, okay? So I've got here, I built a little sample, okay? So this is the box that I'm sampling from. If you look, so there are some red X's, some yellow squares, some green circles, some blue triangles. And what I want to know is, what is the probability of drawing 1 red X, 1 blue triangle, and 1 green circle? And I'm sampling with replacement. So this is really nice. Again, so kind of like what we did in the last thing, I want to know, well, how many options do I have? So if I count, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah, there are 13 things in there. So 13 objects, and going to do some division. And so I want to know, okay, let's start with the first one. What's the probability of drawing a red X? Well, there are 3 red X's in there, so I have 3 chances of 13 of drawing a red X. So, right, I would reach in and I would pull out the red X, look at it and say, oh, look, I got a red X, and then I would replace it, stick it back in there, okay? So the important thing is that in between each draw, I'm replacing whatever it is that I drew, okay? So 3 out of 13 chances to draw a red X. Okay, so then the next thing, all right, to draw a blue triangle. Well, I still have 13 things in there, and that's the important part of this, right? I put the red X back, So I still have 13 things in there. Okay, so now what's my chances of getting a blue triangle? Well, I look at there are 4 blue triangles, okay? So I have 4 out of 13 chances, okay? And then I put the blue triangle back. And then I look again and say, okay, green circle. Well, I have 2, still 13 options, 2 out of 13 chances to draw my object out of there. And so now looking at this, going forward, let's see, let me grab my calculator here so that I can do the math.
Daddy?
Got my calculator out here to do the math. Let's see here. Since these are all independent events, meaning the drawing of one doesn't affect the other, we can multiply these probabilities to find the total. So multiplying across the top gets me 24. And then multiplying across the bottom, or essentially I have 13 cubed. I have 2,197 here, and then dividing those two, I have, the chances of this happening is 0.0109. Okay, so that's the probability. Or if we were looking at this in percentage, right, you have 1.09% chance of, if this is your arrangement, of reaching in, drawing a red, putting it back, drawing a blue, putting it back, drawing a green, putting it back. 1.09 chance of pulling out that combination. So we're looking at it, and so that's with replacement. So not very great chances, right? If we want to get this arrangement. But that's kind of how this works, is you look at your set of available options, you find out, okay, how many are there, and that's the nice thing about this one, is this is really the kind of easy one, because with the denominator here never changing because we replace the thing that we're sampling, it makes what we're doing in this section a little bit easier, okay? So, so let's look at what it's like in the next phase. So if we're doing it without replacement, okay? So in this space, okay, there are 2 different ways to look at this. So again, the same question, what's the probability of drawing a red X, a blue triangle, and a green circle? Okay, so the first way to look at this is, and this matters, right? The order matters. Do I want to know just what is the chances of drawing a red X, a blue triangle, and a green circle? But the order doesn't matter at all. I just want to know what's the chances of getting those 3 things out without putting anything back? Or does the order matter? Okay, so let's look at the first scenario where the order does matter. Okay, and so in that scenario, let's say, okay, I want to first reach in and draw a red X. So I have 3 out of 13 chances to reach in and draw out a red X. Okay, because there are still 13 things in there. And then I want to say, all right, and again, so I reached in and I drew out a red X. And so now that one of those red X's is gone, okay? And so now let's look and say, okay, so what are the chances now of drawing a blue triangle? Well, there are 4 blue triangles in there. But now how many objects am I choosing from? Well, there's only 12 because I pulled something out. So now I've changed the probabilities, right? The chances of me drawing something different, drawing something new is different now, okay? And so then let's look, okay, so what are the chances of me, okay, so I drew out a blue triangle, so now one of those blue triangles is gone. So now what's the chances of me reaching in and drawing a green circle? Well, there are 2 green circles in there, and now there's only 11 other objects for me to pick from. So I have a 2 out of 11 chance of getting a green circle, right? And then if I multiply these together, so if I go across the top, so 24, and then multiplying across the bottom, 13 times 12 times 11, 1,716. And now divide these two. 24. So 0.0139. Okay. Or, right, a 1.4% chance, if I round in there a little bit, a 1.4% chance of reaching in, sampling without replacement, to draw a red X, a blue triangle, and a green circle in that particular order. Okay, if I have to draw it out in that order. Now notice that my chances are a little bit greater to do this, sampling without replacement, than when I sampled with replacement. Just a little bit better. And that's because the things that I'm having to contend with each time is getting smaller after every time I make a selection. All right? Now, the way that we see in some of the learning objectives is they look at it where the order doesn't matter. I just want to know what are the chances, regardless of the order that I draw these things out of getting a red X, a blue triangle, and a green circle. So this is a little bit more complicated because, for example, let's say you reached in and drew a green circle, and then you reached in and drew a yellow square, which doesn't even account for anything, and then you reached in again and you drew another yellow square, right? So because the order doesn't matter, it changes your options. Okay, and so the best way to work out these is the book actually gives us an equation to use. And this equation has to do with building choices. So for example, I want to know how many different combinations, okay? If I just reached in and drew out 3 random things, how many different combinations of 3 things are possible to draw, considering this is what I have to pull from, okay? And so the way that looks is I have 13 things to choose from, and I'm choosing 3, okay? So 13 choose 3. How many different total combinations do I have? And so the way that this works is you take this first number here, so you're going to do 13 exclamation point, and what that is that's the factorial sign, so it's 13 factorial, and I'll show you what that means in a second, divided by, then I look at the next number, the number of things that I'm picking from, 3 factorial times, and then I'm going to do 13 minus 3, and whatever that answer is, factorial, okay? So this ends up being 13 factorial over 3 factorial times 10 factorial, okay? And just as a quick review, what factorial means is, so for example, let's say that I have 5 factorial. Well, that's just 5 times 4 times 3 times 2 times 1. Or if you had, I could look at this and say, hey, look, this is 5 times 4 factorial, right? Because that's 4 times 3 times 2 times 1, right? So that's all the factorial is. It's just a shorthand way of writing out along like a list of descending multiplication events. So our little answer here, it's like I have 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, right? That's really annoying to have to write out over and over and over again. So honestly, it's best if you have most scientific calculators have a little factorial button, and you can just press that and it will do all of that for you. If not, then there are some tricks we can do. And then I'm dividing that by 3 factorial, which is, hold up here. which is 3 times 2 times 1, times 10 factorial, which is 10 times 9 times 8 times 7 times 3 times 2 times 1. Okay, now the really cool thing about problems like this is I can look at it and say, hey, look, here's 10 factorial, here's 10 factorial. All of that divides out. Okay, so really what I have is 13 times 12 times 11 divided by 3 times 2 times 1. And that I can do in my calculator shorthand pretty easily. So 13 times 12 times 11 gives me 1,716 divided by 3 times 2 times 1, which is 6. Now divide those numbers, so I have 1716 divided by 6 equals 286. Okay, so all of that just to find out that there are 286 total combinations of 3, and these are unique arrangements of 3 objects. If I'm drawing out 3 things randomly from this thing, there are a total of 286 unique arrangements of 3 things that can be drawn from that list of things, from that box. Okay? All right, so, and I need this number because I know that in all of my probability things, I take the number of outcomes that I want and I divide by the number of outcomes that are possible, and this is the number that's going to go in the denominator, okay? So now we need to figure out, okay, well, what's the number then that goes up here in the numerator, okay? So now to do that, and again, we're looking at this, we're sampling, so that the order doesn't matter. The way that this works is I want to say, okay, what are the chances of drawing a red X? So I look here, there are 3 red X's, right? 3 red X's, 4 blue triangles, 2 green circles. So I have 3 red X's and I'm choosing 1. I have 4 blue triangles and I'm choosing 1. I have 2 green circles and I'm choosing 1. So I'm using the same exact trick, except for now my numbers are smaller, so this is going to be much easier. So this is going to be 3 factorial over 1 factorial times 3 minus 1, which is 2 factorial. And then again, here I'm going to have 4 factorial over 1 factorial times 4 minus 1, which is 3 factorial, and then I have 2 factorial for this one, over 1 factorial, sorry, my handwriting is getting sloppy, times 2 minus 1, which is 1 factorial, okay? And again, so this would be 3 times 2 times 1 over 1 times 2 times 1. Notice that that would divide out, leaving me with just 3 in this case. Here, and if you pay attention carefully, right, this on the top, I'm going to have 4 times 3 times 2 times 1 over 1 times 3 times 2 times 1. That divides out, leaving me with just 4. The same thing's going to happen here. It's going to leave me with just 2. Okay, so I have the answers to these 3 things. So then to find the total number of options that work for me, I'm going to take, you would take these answers here. So I'm going to take 3 times 4 times 2. Oops. So there are 24 combinations that work. Oh shoot, I erased the number that I had from before. 24 combinations that work. Hold up. So 24 combinations that work. And before I had, let's see, that was 13 times 12 times 11 divided by the 3 factorial, 286. So 24 out of 286. So 24 combinations that work over 280, a total of 286 combinations that that are possible. And I divide those, so 24 over 286 gives me 0.0839, or that's approximately 8.4% chance of drawing, so sampling without replacement, of drawing a red X, a blue triangle, a green circle, again, not caring at all about the order with which these things come out of the box. So that's kind of how those problems work. And the factorial thing can be annoying, but if you have a scientific calculator, which either I think the software just has available for you, or if you just have one, they normally have a factorial button, a little exclamation mark that you can just use. And that'll make your life a little easier. Or you can do my little cancellation trick to make your multiplication things a little bit shorter, okay? So then for the next one, the last thing we want to talk about are mutually exclusive and independent events. And in this one, I need to explain a couple of the symbols that you see in statistics. So for example, sometimes you'll see something that looks like this, where they'll be asking about the probability of A, and then they have this weird thing, B, okay? Or they'll do it like this, where they have the probability of A, and then they have it the other way. Well, it's just B, okay? And in the top case, this is called an intersection. And in the bottom case, this is a union, okay? And so the easiest way for me to understand this is to look at like Venn diagrams. So for intersections, right, if this is A, like everything that is in A lives in that circle, and this is B, everything that is in B lives in that circle, well, right now, these circles are totally separate. There's nothing, they don't intersect at all. So if this was the case, where A is here and B is here, the intersection of A and B would be 0, right? There's nothing. They're mutually exclusive, right? Because there's nothing in between there, right? There's nothing hiding on the inside. On the other hand, I could draw it like this, where here's A and here's B. Well, now there is something in the intersection, right? This space right here, well, that is in common to both sets, okay? And so I would want to know all of those things. So, for example, if set A it had things in it like 1, 3, and 5, that's a 3. And if set B had 4, 2, 1, and 5. Well, what do they have in common? Well, they have a 1 and a 5 in common, right? That would be the things that are in there. The 3 is not common for both, and neither is 4 and 2, right? So that's what the intersection is talking about, right? What do the two things that I'm looking at have in common? And in statistics, there's a couple of ways, excuse me, to think about that. For events that are mutually exclusive, and I want to know what they have in common, right? That's 0. This would be this case, right, where they're separate. A and B are separate, so that's they have nothing in common, right? So the intersection of them would be 0. But if they do have something in common, so if they're like this, and the events are independent, A and B, well then the intersection, or the probability of A intersect B, oops, I drew that the wrong way, of A intersect B is just, we just use the the multiplication rule, right? It would be the probability of A times the probability of B to get the probability of the things that are in the middle, right? The things that are in between them. Okay. Last one to look at is the union. Okay. And so the union is what are the events that belong to one or both of the sets, right? What's in it's like I'm looking for all the unique values, okay? So for example, if I go back, if my sets are 1, 3, and 5, and the other set is 4, 2, 1, and 5. Well, okay, so what's the union? Well, what's in both? Well, there's a 1 in both. Well, and it's not even what's in both. It's just what's there. Notice there are 2 1s there, but since I have one, I don't need the other one because I already know that there's a 1 in any of the spaces. There's a 2, there's a 3, there's a 4, there's a 5. And so these are all the things that are in one or the other. And notice that I don't need to double count the 1, but this is just me looking and saying, okay, well, what's over here and what's over here, and then I'm going to bring them down, and this is the total list of the things that are in each without duplicating anything, okay? And so the way that we calculate that, and now this, and so you may have seen this equation as they say, okay, so the union is going to be, well, it's just the probability of the things in A plus the probability of the things in B, minus the things that they share, right? Minus the probability of the things that are in the intersection. Because if I take A plus B, that counts up everything, and it includes all the doubles, and so then I'm just going to subtract out once the things that they have in common so that those doubles don't appear. Okay, so it'd be like, if I looked at just this list, I would have both of the 1s, and then this just tells me, well, take out the 1. Okay, so a quick example of this. So I have this problem. Given that the probability of A is 0.2 and the probability of B is 0.6, what is the probability of the union, right, of A and B? So what is the probability of the union of A and B? Well, I know that this thing equals the probability of A plus the probability of B minus the probability of B intersect A, or A intersect B. It doesn't... The order of that doesn't matter, okay? But it does matter if they're mutually exclusive or independent, okay? If the events are mutually exclusive, then that means I would get this. I would get 0.2 plus 0.6, which is 0.8, right? Minus, and then so this is the thing that's going to change. If they're mutually exclusive, that's a 0. Because that means that they have nothing in common. And so this would just be the answer, and you're done. But if the events are independent, well, then I need to take 0.2 and multiply that by 0.6 to find the value of the intersection. And that's when the things are independent, right? So if they're independent, then I need to take 0.2 times 0.6, and I get 0.12, and I'm going to stick that over here. So I'm going to get 0.12 when they're independent, and I'm going to subtract, right? And that's going to leave me with 0.68 as the probability of the union. So that's a little bit on mutually exclusive things or independent events and how that works. Let me know if you have any more questions about this stuff, and have a great week. Thanks.